start in 2 or 3 minutes. Okay, I think people are coming more or less. Okay. So, but before we start this last session of the conference, I will make one announcement. So, 2 talks by Mikhailovsky and Strom have been cancelled for, acceptable reasons. Therefore, according to the program, so meeting should go immediately after your email because the 2 talks are cancelled. Okay, if you hear me. And now we can start. So I will announce the first talk of the session. It will be given by Gaban Grégoire, and the talk is entitled Circumventing the Miscibility Gap in GAN's nanowires using HVP growth and kinetic modeling. Please.
Thank you for the introduction. So first, I would like to thank the committee for giving me the opportunity to present the work we have done in our laboratory, which is Institut Pascal, located in Clermont-Ferrand. So the topic of my presentation will be the growth of indium gallium arsenide nanowire growth using HVP. So first, I will quickly remind our experimental setup and also the basics of HVP, already introduced by Evelyn Gilles this morning. Then I will quickly go to the results with first the growth of indium arsenide and gallium arsenide nanowire grown by HVP, and finally the growth of indium gallium arsenide nanowires. So at Institut Pascal, we have a customized HVP reactor. So the reactor is made of quartz, divided into 3 main zones. The source zone, where are produced the 3 elements, which are 3 chloride. So we flow HCl over a liquid metal at high temperature. Then we have the mix zone, in which are introduced the 5 elements, which is arsine, and arsine is fully decomposed into IS4 at high temperature. And finally, you have the growth zone. So as Evelyn Gilles said this morning, HVP is a near equilibrium process, meaning that it quickly returns to equilibrium. And the main factor is the supersaturation, which is given by the ratio of the equilibrium constant calculated using the Gibbs-free energy and the constant calculated using the ratio of reactant and the product of the reaction. So first, we obtained the first result with the growth of indium arsenide on bare silicon. So as you can see, we obtained well-faceted nanowires with 6 equivalent 110 side facets and top 100B facet. The variation of the nanowire length with temperature is typical for HVP, and we observe that we have the same trend as gallium arsenide 100 shown this morning. So this means that the growth occurs through direct condensation of the precursor on the surface substrate surface. Concerning their structural properties, the nanowires exhibit many twins, and whatever the growth condition. So we tried many growth temperature and also a different trifle ratio. And this is mainly due to the arsenic-rich environment of the HVP. In order to grow homogeneous nanowires with homogeneous diameter and length, we switched to selective area growth. So using pattern substrate, we first tried on gallium arsenide 111B substrate, since it is easier to nucleate on gallium arsenide substrate. So first we have to determine the ideal pattern. So we first study the effect of the opening diameter. As you can see on the first figure, for large diameter, we have a growth of a poor quality 2D layer, which is due to the coalescence of many 2D ions that nucleate in the openings, while for smaller diameter, so here 60 nanometer, we have the nucleation of only one nucleus in the opening, which results in nanowire growth. Then we switch to larger array, and we can see that we are able to grow a dense array with homogeneous nanowires. Concerning the growth mechanisms, we can see that as a function of the temperature, we have the same behavior as the self-induced nanowires, meaning that we have the same mechanisms, which is direct vapor-solid growth mechanisms. Of course, since it is more interesting to grow nanowires on silicon, we switch to silicon substrate. And the same study was conducted with in order to determine what is the best pattern for to grow nanowire. So as you can see, we observe the same trends as for gallium arsenide substrate, with so a growth of a 2D layer for large opening and nanowire for smaller ones. The main difference with compared to gallium arsenide is that we have nanowire for larger opening, and this is due to the reoxidation of the openings after the HF etching before the introduction in the reactor. Then, as for gallium arsenide substrate, we switch to larger array, and we are able now to grow nice arrays of indium arsenide nanowires. Then we conducted a study as a function of temperature and also trifle ratio in order to see if we were able to control the morphology of the crystal. And as you can see by on the first figure, by changing the temperature, we can switch from platelet to nanowire. So at low temperature, we have a low axial growth rate, which is due to a low kinetics of decomposition of the precursor, while at higher temperature, we increase this kinetics, so the nanowires are longer. And for the trifle ratio, by increasing the element 3, so here indium chloride, we have a saturation of the 101B surface at this growth temperature of 640 degrees. So as the decomposition is slow, we have a low growth rate, and we are able to switch from nanowires to platelet also by changing the trifle ratio. Encouraging by those results with the growth of indium arsenide on silicon, we tried the growth of gallium arsenide on silicon. So here you have two different diameter of openings, and as you can see, so for small openings we can have nanowires. We also well-defined side facets and well-defined side facets. And the growth of the nanowire is also due to the nucleation of only one nucleus in the opening, which results in nanowire growth. While for a larger opening, we have the growth of many nuclei, which result in coalescence after, which result in a platelet after coalescence, and these results are very interesting for conformal growth, and that's what the results that Evelyn Gilles showed this morning. Such behavior has already been observed in MOVP with the growth of gallium arsenide on silicon. So concerning their structural properties, so the platelet exhibit a defect-free lateral overgrowth. The interface between gallium arsenide and silicon is quite good, and we can observe some dislocation in the center of the opening, which are the result of the coalescence of the nuclei. For the nanowire, we can see that we have many twins, and this is typical for gallium arsenide material along the 111B direction. And it is known that the twin density is sensitive to the arsenic environment and also temperature. So it will be interesting to study the effect of the arsenic and temperature on the twin density. Then, since we achieved the growth of indium arsenide and gallium arsenide material, we decided to try the growth of indium gallium arsenide. So first, I started by using indium arsenide growth conditions, so with indium-rich environment, and then by adding some gallium. So as you can see, by increasing the gallium partial pressure in the vapor phase, we have a decrease, so from the right to the left, a decrease of the nanowire length and an increase of the diameter. And this increase of the decrease of the nanowire length with the gallium chloride partial pressure is due to a saturation of the top surface with gallium chloride molecules, which slowly decomposed at such growth temperature. Concerning their composition, we can see that the composition is constant along the nanowire, and that also that by increasing the gallium chloride partial pressure, we can tune the composition from 15% to 25% gallium concentration. And the fact that the composition is constant along the nanowire is also due to the fact that in HVPE, the surface diffusion is negligible compared to MOVP and ABE. So this result is quite interesting. Here you have a summary of different growth conditions that I tried to grow indium gallium arsenide. So at high temperature, we can see that we can have decomposition of the material, which is due to the weak indium arsenide bond at such growth temperature. And at a standard growth temperature, we can see that the gallium concentration deteriorates the crystal quality. So this means that in order to tune the composition and keep a good morphology, we have to optimize the growth temperature with the vapor phase composition. Finally, we wanted to link the vapor phase composition to the solid composition. That's why we tried to model this. So the first we suppose that the ratio of concentration of indium and gallium is proportional to the ratio between the indium arsenide growth rate and gallium arsenide growth rate in the ternary material. So this gives us a relation between the declination energy of gallium chloride and indium chloride with the vapor phase composition, the equilibrium constant of each binary, also the interaction parameter in the ternary material, and the composition of the solid. Finally, we can have a relation that links the partial pressure, so indium chloride partial pressure, gallium chloride partial pressure, to the equilibrium constant, the solid composition, and the declination energy. And what we can see is that in our case, we obtain the best fit of the experimental point when fixing the delta epsilon to equal to 0, meaning that our composition is simply determined by the thermodynamics through the equilibrium constant in the ternary. So to conclude, we show that the growth of indium arsenide and also gallium arsenide and indium gallium arsenide occur through direct condensation of the gaseous precursors. The morphology of the crystal can be tuned by changing the growth condition, but also the pattern design. This morning, Evelyn Gilles showed that conformal growth of 3 years nanometer is possible. And finally, we show that growth of indium gallium arsenide is possible with tunable composition. Thank you for your attention.
Thank you, Gabon. Excellent talk. Thanks. So, but for the circumventing the miscibility gap,
yeah,
because your talk is called circumventing the miscibility gap in gas. But of course, the temperature is high.
Yeah,
it's much higher than critical, which, if I remember correctly, is about 543 Celsius for in gas. So yeah, basically circumventing the miscibility gap by high temperature, which is accessible in your technique. I mean, compared to us. So maybe for pedagogical reasons, I would advise, you know, name it like, you know, compositional tuning, wide compositional tuning, but maybe not circumventing, because it's nothing to circumvent. Do you agree? Yeah, thanks. Okay, Alexander, hi, please.
Your micro is off. Your microphone is off.
Thank you for your talk. And I have one question. Have you observed nonlinear dependence of nanowire growth rate versus distance between them due to the competition between the efficiency of decomposition of precursor molecules and the amount of material per one unit of area?
Sorry, I don't know which.
I talk about selective area growth, and do you observe non-linear dependence of nanowire growth rate or length versus distance between them?
No, we have no. There is no influence of the pitch of the arrays.
Yeah, pitch
on the length. So no.
Okay. Okay, but in most CVT, as far as I know, it was observed.
Yes, because of the surface diffusion of the atoms.
Yeah, here there is no surface.
Here we have no absorption. No absorption of the mass.
Okay, thank you.
I wouldn't expect any pitch dependence. Yeah, that's correct. Understandable. Further questions? I don't see further questions. So thank you, Gabon.
Thank you.
The next talk will be given by Alexander Karakin, who is already on the screen. And it's called Modeling of Monolayer Growth on the top facet of gallium catalyzed gallium arsenide and gallium phosphide monolayers, please.
Can you see my screen?
No.
No.
Yeah, it's okay now, you can stop.
Good afternoon, everybody. I am Alexander Karakin. I would like to present my work about modeling of self-catalyzed nanowire growth. This work was performed in St. Petersburg at 3 institutes, at St. Petersburg State University, at Institute for Problems of Mechanical Engineering, and at Academic University. Why do we study self-catalyzed nanowire growth? Because there is an advantage of self-catalyzed growth compared to more traditional growth techniques that use foreign catalyst. In case of self-catalyzed nanowire growth, there is no unwanted incorporation of catalyst material into growing crystal that results in a degradation of properties of crystal. Here is the outline of my talk. Firstly, I will give a short introduction. Mostly, I repeat several points that were in the presentation given by Frank Glass about self-catalyzed growth. Then I'll describe shortly theoretical model, and we discuss results of simulation. So Let me talk now about gallium arsenide nanowire growth. Here you can see a schematic illustration of the system. We have a gallium arsenide nanowire with gallium arsenide droplet at the top, and due to low solubility of arsenic in droplet and due to low small diameter of droplet, we have an interesting effect. The amount of arsenic in the droplet may not be enough to form a whole monolayer. Therefore, three growth regimes are possible. The case A, when the amount of arsenic atoms minus in the droplet minus the equilibrium amount of arsenic atoms is larger than number of atoms in monolayer, we have fast growth due to that is limited by volume diffusion of arsenic. Case B, if the amount of arsenic atoms is not enough, we can have firstly fast growth due to the volume diffusion, and then slow growth due to the vapor flux. These two cases can be realized if there is no truncation of nanowire top face. In case of truncation, we have also the third regime. Firstly, fast growth due to the material into the droplet and due to the formation of additional faces at the perimeter of nanowire top, and there slow growth, growth of facets. So totally we have three growth regimes, and the regime, the presence of the regime depends on the maximal concentration of group 5 in the droplet. So let me introduce this quantity theta max by using this definition. If theta max is larger than 1, we have fast growth. If it less than 1, we have fast growth, then slow growth, and alternatively fast growth and faceting. So the main question that arises here is under what conditions are these growth regimes realized? At the moment we started this investigation, we did not find any theoretical model that would be able to describe slow growth regime. These two models were published later. Therefore, we started with the model published by Frank Glass with co-authors and add consideration of kinetic of island growth. Here you can see a schematic illustration of the geometry considered in the model. So we have a cylindrical nanowire with a spherical droplet on the top. And the growth occurs via formation of disc-shaped island at the nanowire top face. It should be noted that here we do not consider the truncation effect. There is no faceting in our model. But this model allows to find growth conditions where theta max, the quantity that I introduced, is larger than 1 or less than 1. So we can make some predictions about when slow growth regime is possible. So we consider in our model material balance equation for arsenic and don't consider material balance equation for gallium because we consider only steady state growth. So we solve a diffusion problem and in the steady state approximation, and we found by a finite element method that this shape island has a torus diffusion field. Then we looked through the literature and found a known solution for Laplace equation for toroidal for charged torus, and use this solution for our case to derive expression for incorporation flux. So we consider the case of small islands and large islands. So then we compare these theoretical results with calculations by FEM and found that the agreement is good, very good. dot here is the results of VM, and the lines are results of our modeling. So the modeling of monolayer growth proceeds in our model via two stage. We firstly consider nucleation and waiting time, and then a lateral island growth. Here we do not consider the distribution function for waiting time, and I would say we use the deterministic approach and determine the time between two consecutive nucleation event in case if this supersaturation would be constant. Further, we should of course include distribution of waiting time in our model. At the island growth stage, we solve the material balance equation for arsenic together with the equation for island radius. We use expressions for arsenic fluxes obtained in this model and introduce our formula for incorporation flux. So this model allows imitate fast and slow island growth. Here the results for gallium arsenide growth in a fast growth regime and in the combined growth regime. Let me skip so we compared our modeling with experimental work by Ramdani with co-authors and found as a fitting parameter the value of interface in energy. This value is about 3 times larger than in the work in this work. Okay, but okay. Also, we compared to the predictions in our model and in model by Frank Glass for nanowire growth rate and obtained a qualitative agreement. This model allows to plot the dependence of theta max versus nanowire radius, total arsenic flux, and temperature. For example, for a high temperature growth of gallium arsenide, we can find a region, it is highlighted, where a slow growth is possible. So we see that slow growth can be observed in case of small radius and relatively small arsenic fluxes. The dependence of arsenic concentrations and nanowire growth rate versus growth conditions are plotted that are in agreement with previous modeling. We proved that this scaling law for theta max that was already found in this work, theta max scale is proportional to nanowire radius for not too small radius. So if we decrease the temperature, the area where slow growth is observed increases much, and we see that already for 20 nanometer nanowires, we can observe slow growth. Similar results were obtained for gallium phosphide. The difference is that the region where there is no growth move in the direction of high phosphor fluxes because we have more evaporation in case of gallium phosphide. And also the nanowire growth rate is smaller in case of gallium phosphide due to higher desorption of phosphorus. And the last point of the presentation, we obtained some estimation for evaporation coefficient of phosphorus. In the previous work, the evaporation coefficient for arsenic was obtained, and the conversion coefficient for arsenic was obtained too, but not for phosphorus. We used results, experimental results that we obtained at academic university for on the growth of gallium phosphide nanowires, here are some details, and obtained the value of re-evaporation coefficient. That we found that it can be larger than the evaporation coefficient for arsenic. Also, we found some correlation with surface density of nanowires. With increase of surface density, we have an increase of re-evaporation coefficient. So to conclude, we obtained new expression for the growth rate of disc-shaped island model. Our model is in a good agreement with experimental data. Two growth regimes can be described within our model. We make some predictions for growth regimes for gallium arsenide and gallium phosphide nanowires, and we estimate the value of the re-evaporation coefficient of phosphorus. Thank you very much for your attention.
Thank you, Sasha. So for the nice talk, let me clarify something.
Yeah.
So you are modeling nanowire with a nanowire with planar interface.
Right.
Right. So it's world side.
Yes. Yes.
So then the nucleation occurs not in the center, but at the triple phase line, or even
yes, of course,
at the corner.
Of course,
of the hexagon, as in C2N parallel. And can you show the expression for the waiting time? I think it was proportional to R squared, inversely proportional to R squared.
Right, because Tn is
yeah, but what is that? So this is given by a nucleation probability, but it's not proportional to R squared in this case, because it's not center nucleation. So I think this should be changed.
I
you know what I mean? Because it's not a center nucleation, so it's not all the area of the
understand,
top
only
facet,
periphery, or the line between
periphery,
the
or even the corner,
yeah.
or even the corner, as again in this parallel. So I think this can be refined. Okay?
I agree with
Frank,
you.
Please. Frank.
Yeah.
Yeah.
Yes.
Hello.
Hello again. I have two questions, I think. You estimate large re-evaporation coefficients, and you said that this increases when the density of the nanowires increases. So does it mean that re-evaporation is mainly from the sidewalls of the neighboring nanowires rather than from the substrate, or am I going too far?
Thank you for your question. Truly speaking, we didn't analyze much this dependence, but I think, yes, it means what you said, yes.
And my
also
second...
you see, sorry, you see some, we don't have enough data to make some conclusions. Also, you see that the radius changed here.
All right, and to be clear, the epsilon say equals 7, so this means that there is 7 times more arsenic atoms which get into the droplet from re-evaporation than from the direct flux. Yeah. So my other question is, of course, I'm very interested by your determination of the edge energy. So we keep in mind the remark just made by Vladimir, with which I agree. But do you have any simple idea or simple explanation why there is a factor of 3 between our estimates?
But between what factor?
Between the, as you mentioned, that it's about 3 times larger than the value that I estimated in the past with a different model, admittedly, but from experiments. And so, is there any simple? Maybe it's a silly question, but is there any simple explanation why?
But it's a huge difference. So it's a huge difference, 3 times. Yeah.
Because what I maybe add is that I've been modeling the statistics of the growth of Wurtzite layers, and doing this, which is nearly finalized, the paper is nearly finalized, that I cannot really get one single value for this edge energy, but I also tend to find larger values than what I estimated in the past. So maybe closer to 0.3, 0.4 as you find. So that's very interesting, very interesting to me.
Only so it's really a very difficult question to answer, because we are talking about the edge energy of one monolayer system to support partly this value. I can say only that this value is correlates somehow with the calculation of surface energy for planar interface made by density function method by Kretzer and Sakong, you know.
Yes, I know, but I mean, I'm always a bit dubious about this because it was an interface between the crystal and between a gold, planar, but not really planar between, say, 3.5 semiconductor and liquid, but between 3.5 and I think gold gallium crystal.
For simplicity, we should count the number of bonds that we have at the island tension compared with the number of bonds on planar interface, and so it should depend on the reconstruction on this age.
Yeah, and
maybe it's not the difference into the number of bonds not differ not too much.
Yeah, my question was really not about the calculation, but if there was any simple idea why the estimates are very different. But I guess it's a question without an answer, a simple answer.
Yeah.
Thank you.
Okay, thank you.
Are there any further questions? I don't see any, so thank you, Sasha, again.
Thank you.
So the next talk will be presented by Vera Lendishova, and it's on the effect of etching on structural, properties of, I'm sorry. Of gallium nitride nanowires grown by selective area MB.
Hello, may I start the demonstration of the screen?
Yeah, now Sasha, you have to turn off your screen to let Vera share her screen. Sasha, can you turn off? No, we are still seeing your screen. Could you please turn off your screen? Yes, thanks. Vera, now you can share your screen.
Do you see my screen?
Yeah, we can see your screen. Okay, we can hear you, so please start.
My name is Vera Lendishova. I'm a bachelor student of Alfyorov University. And the topic of my work is effect of wet potassium hydroxide etching on structural properties of gallium nitride nanowires grown by selective area growth MB. In this talk, I shall first explain the motivation of the study. I shall then present an experimental part, the sample synthesis and chemical etching. Then I will concentrate my talk on identification of nanowires polarity and impact of etching time. And finally, I shall submit the main conclusion of my work. 3N nanowires are promising direction of studies for manufacturing like emitting diodes, sensors, transistors, solar cells, and water splitting cells. combining 3N nanovirus with cheap silicon technology is highly important for the practical application of these structures. However, growth of 3N nanovirus on silicon substrates is often accompanied by a high density of nanovirus up to their full coalescence. As a consequence, this imposes restrictions on the creation of radial core shell heterostructures based on 3N materials. In particular, they can help to decrease the adverse effect of Fermi level pinning and increase the active area of light emitting diodes. Those researchers are paying attention for the development of selective area growth. In this slide, you can see on this slide, you can see the difference between the classical growth of nanovirus and selective area growth, which is in the use of the substrate with pre-coating inhibitor layer with ordered holes with defined density, location, and size. The figure on the left illustrates the main stages of selective area growth. At first was formed the silicon oxide layer on the silicon wafers by thermal acidification in the atmosphere at a temperature of 850–950 degrees Celsius. Holes were then formed in the oxide layer using the photolithography through arrays of silica microspheres and dry etching to delay the photoresist. In the figures on the right, you can see a typical SEM images of the surface of patent silicon oxide silicon substrates. The average diameter of the holes is 300 nanometers, and the average distance between them is 1 micrometer, which determined by the diameter of the microspheres was used. I'm sorry. This slide shows the typical SEM images of gallium nitride nanovirus arrays synthesized on patent silicon oxide silicon substrates at different substrate temperatures. As you can see, the morphology in the range of growth temperatures between 815 and 820, gallium nitride nanowires are formed both on the silicon in the holes and on the inhibitor layer. The growth mode of the selective nanowires is achieved by increasing the substrate temperature to 825 degrees. At a higher temperature, nanowires were not formed. The data of graphs show that heights and diameters of nanowires formed on silicon exceed the ones formed on silicon oxide, and with the increase of substrate temperature, the heights and the diameters of nanowires on the both surface linearly decrease. However, the possibility of the selective area growth of nitride nanowires over a large surface area is hampered due to the narrow growth window, as shown on this slide, and a large temperature gradient along the surface substrate in typical MBA stub. For example, in the case of high temperature growth, this gradient is about 20-25 degrees Celsius. In this account, the application of selective area grown nanowires is difficult. A possible solution to these challenges is the selective chemical etching. It is known that wurtzite nitride semiconductors exhibit different polarity surface along the growth direction. What should be noted? Is that different polar surfaces interact differently with the potassium hydroxide solution. In this regards, it is possible to achieve selective etching of gallium nitride nanowires with a certain polarity using potassium hydroxide. In this slide illustrates the scheme of etching experiment. Selective etching of gallium nitride nanowires on various substrates were carried out using a potassium hydroxide aqueous solution 125 at temperature of 75 degrees Celsius with duration from 1 to 7 minutes. Wet etching of nanowires proceed via the reaction you can see on the right. For the first, we have identified the polarity of the nanowires on the different substrates. On this slide, you can see the SEM images of the initial GaN nanowires and ones after 1.5 minutes of etching. As can be seen, the etching process significantly change the morphology of nanowires grown on the silicon oxide. Impact of the etching solution led to the formation of pyramid-like tops of the nanowires, and we can conclude that nanowires grown on silicon oxide are nitride polar, and nanowires grown in the holes on silicon are gallium polar. So we have studied the influence of etching time on the morphological properties of the nanowire. On the figures, you can see 3 stages of the etching. The morphology of the sample before etching and after 1.5 minute etching and after 7-minute etching. An increase in the etching time leads to the decomposition of gallium nitride nanowires on the inhibitor layer until they are removed. To summarize what I have said, on this slide, you can see the main conclusions of the presented study. Thank you for your attention. I shall be pleased to answer your questions.
Thank you very much, Vera, for the nice talk. So I have a small question. Can you please show your page 5 of your presentation? Page 5.
A second. Page 5, yes.
Yeah, this one. Here you have a nanowire diameter and nanowire length versus growth temperature. Okay.
Yes.
And they both decrease with temperature. Do you know why? What is the reason for that?
Because with the growth of the temperature in the MB machine, what we used, the flux of gallium didn't enough for formed nanowires, because gallium desorption from the surface of
of course it's due to desorption of gallium at higher temperatures. Thanks. Thank you. So I don't see any further questions, so we continue with the talk of Boris Grubakin, and it's entitled Exciton and exciton charge carrier interaction and exciton collisional broadening in gallium arsenide aluminum gallium arsenide quantum belts. Please, yes, we can see your presentation, so you can just start.
Right. Hello, everyone. I would like to preface the talk that I'm about to give by saying that once I saw the program of the conference, I realized that this is seriously off topic, actually, compared with all of the other talks in the conference. But well, since I'm here, nothing left to do but to talk about it. So I will just proceed. So the work that I would like to talk about is devoted to the problem of exciton charge carrier interactions and the effect that these interactions have on the exciton collisional broadening in quantum wells. Right. I will give a small introduction into the problem, and then I will go over the different steps that are required to carry out the analysis, and after that there will be a small discussion, and then I will talk about some of the conclusions that can be drawn from our work. Now, what the primary thing that allows investigations of interactions between excitons and other quasiparticles is the fact that modern day heterostructures can be of very high quality, which is reflected in the fact that the lines of exciton resonances are determined entirely by homogeneous broadening. So and this homogeneous broadening is composed of two parts, the radiative part and the non-radiative part. The radiative part is due to the fact that excitons have a finite lifetime in any sort of heterostructure, and the non-radiative part is due to the fact that excitons may experience interactions with other quasiparticles or maybe defects in the structure while they exist before they recombine. So by studying the behavior of the non-radiative broadening with respect to certain experimental parameters like the pumping power or the polarization or the temperature, for example, we may get a glimpse into the physics behind the interactions between the different quasiparticles. So this is why it's fundamental. There's a fundamental interest in studying these interactions. Now, if we're talking about interactions between quasiparticles and line widths, whatever, we are basically talking about scattering theory. If we're talking about scattering, then we immediately have to specify what sort of scattering channels are we going to include in our treatment. We will be looking at excitons being scattered by other excitons, as well as electrons and holes in three separate cases. These are the interaction types that are most common in optical experiments. We will be assuming that the temperatures are very low, so these are cryogenic temperatures, helium temperatures, and this will allow us to neglect all of the scattering channels in which either of the interacting particles is excited to the next subband. So all of the scattering will take place in the ground state subbands. And as a result of a scattering event, the momenta or wave vectors of the particles can change, as well as their spins. Right. So if we're talking about scattering, quantum mechanical treatment is of course necessary. So that's why we need to obtain the wave functions somehow. And this is actually a point where the limitations of most previous studies become very apparent. Actually, studies of interactions between quasi-particles such as excitons have been carried out for over 40 years, but well, as late as 10 years ago, the computational difficulty of the problem introduced some constraints into all of those works. And these are mostly that researchers used very simple model wave functions like 2D wave functions or analytical wave functions with variational parameters. So more accurate wave functions, it's interesting to see what more accurate wave functions could change in the scattering. But another thing is the more significant limitation is that usually only a single structure was considered in all of the theoretical papers. So this did not allow to track how the parameters that the researchers calculated vary with varying parameters of the structure. So using an approach which is based around a finite difference method around diagonalizing an exciton Hamiltonian, we can find the wave function of an exciton in an arbitrary quantum well, and then we can track the quantum well with dependence. So here's just a pretty picture of the slices of the exciton wave function in different parts of the quantum well. And here's a picture which showcases how well the oscillator strengths predicted by the theory are aligned with experiments. Now that we have the wave functions, we are obliged to calculate the scattering matrix elements. To do that, we combine the wave functions of excitons, or electrons and holes, into a Hartree-Fock anti-symmetrized wave function. And from the structure, the analytical structure of such a combination, we can separate the matrix elements of the scattering into several terms with distinct physical meaning. So in the exciton charge carrier case, we have a direct term and a fermion exchange term. While in the exciton case, we have 4 terms because one of them is the direct electrostatic term, while the 3 others are the exchange terms. This, I'm not sure if you can. All right. This is the boson exchange term in which both electrons and holes are exchanged simultaneously. And these 2 are the fermion exchange terms in which only an electron or only a hole is exchanged. At very low temperatures, when all of the initial wave vectors can be assumed to be 0, then these 2 integrals and these 2 integrals are equal to one another. And so these will be referred to as the direct integrals, and these will be the exchange integrals. It's been shown in many previous works, and then it's true in our work as well, that the exchange integrals are actually the primary contribution to the interaction. And in fact, they dominated the interaction so completely that we can actually just use the exchange constants to quantify the strength of the interaction. In particular, we can estimate the energy shift of the exciton resonance by using these exchange constants simply by multiplying them by the quasi-particle density. Here in the picture, in the figure, you can see the dependencies of the different exchange constants for excitons and electrons and holes with respect to the quantum well width. You can see that there is a broad maximum around 25 to 50 nanometers, so this is not typically the range of quantum well widths where you would expect to see a maximum of anything, but this is due to the fact that these integrals are 2-particle integrals, and so of course their behavior is different from say something like the binding energy of an exciton. Right, so now that we have the matrix elements, we can use them to calculate various physical observables. We're concerned with the collisional broadening. I'm not really gonna go and describe everything that's in the formula, it's just boring. But an important thing is that at very small particle densities, the broadening is linear with respect to density, with a constant that is proportional to the exchange constant squared. While at very large densities, the behavior of the broadening is, well, it's proportional to the square root of the density. So these equations can only be solved numerically, even in the simplest of cases. But yeah, so here are the results, and you can actually see that the broadening does start out as linear, and then it becomes sublinear as the densities increase. Now, the momentum distributions of the particles that we've used, they basically don't exist because all of the particles are at q = 0 because the temperature is 0. But the spin distributions we still have to specify. So here we have considered two limiting cases. One of them is the completely unpolarized case where all spin states are populated equally, and the other one is when only a single spin state is populated. And you can see that in the exton-exton case, there is a pretty large difference between these two cases across all quantum well widths, while in the exton charge carrier cases, there is basically no dependence on the polarization. But these are numerical curves, and it's difficult to quantify like what changes when we vary the quantum well width. We see that something's happening, but we can't really quantify it. So to do that, we've employed a simple model two-parameter functions, which we've come up with based on the asymptotics of the original equations. That's two parameters are sigma 0, which is the linear cross-section. So it's just the slope of the broadening in the linear regime. And n0 is the critical density, which indicates the particle density at which the broadening becomes essentially sublinear. So the larger it is, the longer the dependence is sublinear, and so the larger the overall interaction is. In the figure, you can see the results of fitting this function to the numerical data, and you can see that the sigma 0 parameter actually follows the quantum well width dependence of the exchange constants, as we would expect, and the critical density decreases with increasing well width, which is consistent with the exton's radius decreasing in larger wells. Yes, so and now that we have the exchange constants and we have the dependence of these parameters in the quantum well width, we can actually use this to compare our data to experiments without having to deal with the particle densities, because the particle densities are very difficult to establish accurately from experiments. And this is actually a serious limitation in all of these studies. But if we compare the ratio of the shift to the broadening in the linear regime, then this ratio doesn't depend on the concentration of the particles. And as such, it's a good way to compare theories with experiments. So our data estimates this ratio to be from 5 to 13 approximately. So it's something like half an order of magnitude, an order of magnitude. And this is consistent with the experimental results that we have found in this paper, for example. So you can see that the shift is in the order of 20 microelectron volts, while the broadening is closer to 100 at very low temperatures. So to compare our data to higher temperatures, we would need to take the momentum distributions into account, which is very difficult computationally, but is possible. And so that's probably going to be our next step. But as of now, we have obtained the, you can just see what's on the slide. So thank you for your attention, and I'm ready for some questions.
Thank you very much, Boris. I didn't quite get where and how temperature enters your equations.
Right, that's because I skipped over the equation part. So this is, you could say, the master equation for the broadening. And the important thing here is this quantity, which is the number of particles that scatter the excitons. Now, this number depends on the wave vector, and on the spin of the particles that we're talking about. So essentially, this is a distribution function.
Mm-hmm.
So if Q is like a momentum, then a certain temperature corresponds to a certain average momentum of particles. So it could be a Boltzmann distribution or a Fermi distribution for electrons.
I see.
But so this is where it comes into play. In our case, this is just this just doesn't depend on the wave vector, only on the spin.
Mm-hmm. And can you enhance collisional broadening by temperature? Or otherwise, I mean, other way around, I don't know, because usually collisional broadening depends on temperature.
Well,
in other systems maybe, but
no, I think
from what I've studied.
Yes, I think it should depend on the temperature, but how and why it depends on the temperature is a good question, because if we're talking about the equilibrium state without any pumping, then at higher temperatures there's simply more extons existing in equilibrium. So that could be one source of it. But if we're talking about optical pumping, then I think that if we isolate the effect of the pumping from the effect of the exton density being higher simply from the temperature, then it shouldn't actually be that big of a difference. Is my opinion.
For my curiosity, where have you got your beautiful English accent?
I have had the good luck to live in America for 3 years when I was a little kid. So that's
okay. Where in the United States?
Mostly New Jersey, Philadelphia, New Jersey, something like that.
Thanks. Great. Nice to hear. So, are there any other questions?
If I may say so myself, your accent is also very pleasant to hear.
I was in Oxford.
Right. I can hear it.
So, are there any other questions in the audience? I don't see any, so we move on. Thank you very much again. So the next talk will be given by Yuri Eremeev.
Yeah, thanks.
And it's entitled Elastic Properties of Porous Silicon Layer on Hybrid Silicon Carbide Silicon Substrates. Please.
Yeah, you're right. Sorry. Do you see the presentation?
Yes, we can see the presentation. We can see you, so you just start.
Thanks. Okay. Recent years, silicon carbide became the most promising material for the power semiconductor devices. So CC can operate at high temperatures and under the influence of ionizing radiation. Monocrystalline silicon carbide thin films can be synthesized on silicon by the atomic substitution method, which was made in Institute of Problem of Machinery. You can see the CC hybrid substrate with the thin CC film on the silicon substrate. So in this work, the elastic properties of the macroporous silicon layer are studied, which was formed during the growth of CC film. First of all, the usage of CC is concentrated in the growth of TN materials for the electronic and optoelectronic devices. CC buffer layer effectively relaxes elastic stress between TN materials and silicon, enabling the growth of crack-free thick layers of aluminum nitride, gallium nitride, and aluminum gallium nitride solid solution using HVP technique. The last works show the ability to construct the LED chips using the CC hybrid substrates, and the characteristic size of the chips 500 microns. What we have known about the porous structure under the CC film. So figure 4 presents a typical plot of loading unloading curve acting upon the indenter versus the depth of the penetration. From there, we know that the Young modulus of the porous layer is about 110 gigapascals. At the right picture, you see Auger electron spectroscopy of the SIDC substrate. And we see the non-monotonic dependence of the signal, and which means that SIDC is grown on the porous surface with the different thickness. Next, the residual mechanical strain in the SIDC layer is low, about 0.17%. And the average porosity of the porous layer from the SEM images is about 30%. So the aim of this work is to obtain the dependence of the elastic constants on the porosity of silicon layer. The spherical and octahedral pores of the forms of the pores are investigated. Also, the stress relaxation in the SIDC film is considered. Let's consider the cubic periodicity cell of silicon with the H that equals to H. A porous structure is created by adding randomly arranged spherical pores, left picture, octahedral pores, or the spherical pores with the thin SIDC layer. The characteristic size of the pore is the same for all pores, and the positions do not correlate. The elastic properties of the porous layer are determined by finite element analysis in the frame of COMSOL multiphysics. The algorithm is based on the homogenization approach. The elastic constants of the heterogeneous material are determined by the Hooke's law in the following form, where C is the matrix composed of the elastic tensor components of the heterogeneous material. Sigma and epsilon are obtained by averaging over the deformed cell volume. So to find the matrix, the opposite faces of the cube are successively subjected by the deformation. The displacement of the cube faces takes into account the boundary condition, periodic displacement boundary condition, where distance and source depicts the opposite faces. U is the offset, X is the vectors to the opposite faces, and without deformation is equal to H. So epsilon 0 is the specified strain tensor. The procedure allows one to obtain the required number of equations for finding the elastic tensor components. At the figure 6, you can see the deformed structure with the stress scale bar, and so we average the sigma and epsilon for these structures for the shear deformation and deformations and the density deformations. So the error sources are minimized during calculation: the Finney size effect, discretization error, and statistical fluctuations. In the COMSOL program, the triadrans were selected at the elements of the partition. To estimate the discretization error, the maximum element size increased, having constant relation to the minimum element size. The dependence of C12 elastic constant on the size of the mesh element is shown in the figure 7. It's seen that there's almost no influence of the size of the tetrahedrons on the C12 constant. This is the same for the other constants, and the triangles depict the boundaries of the confidence interval. So consequently, the calculation is provided for the normal COMSOL mesh with the delta over H relation equal to 0.1. The standard deviation of the elastic constants when simulating the system 10 times doesn't exceed 3%. So optimization for the system size is also carried out. The procedure is provided with the constant pore size and different H. So in the case of spherical pores, saturation occurs at H over R approximately 6 and about 4 for octahedral pores. Calculations show the porous silicon to have three independent elastic constants. The dependence of the biaxial modulus on the porosity is shown in the figure. The biaxial modulus in the octahedral pores model is slightly smaller than for the spherical pores. So the biaxial modulus of the porous layer decreases by about 35% for porosity of 30%. Thin CC boundary layer with the thickness with different thickness greatly increases the biaxial modulus. And for the case of the thickness of this CC to over R relation about 0.12, you can see there's almost no difference in the biaxial modulus on the figure with different porosity. So the lateral component of the stress tensor in the CC film is investigated. The following relaxation mechanisms are considered: the reduction of the elastic moduli of the porous layer, that leads to about 1% of the relaxation. The folding of the CC film leads to the reduction of the contact surface, which shows about the same 1% of the relaxation. And the curvature influence is considered in the model. So to conclude, the dependence of the elastic constants of the porous silicon on the porosity is analyzed using FEM. It was found that the porosity reduces the elastic moduli by about 35% for porosity of 30%. However, the presence of the porous layer almost doesn't influence the stress in the CC film. And the results are consistent with the experimental data. Thank you for your attention.
Thank you, Yuri, for the nice talk. So you have considered 3C cubic silicon carbide.
Yeah.
How the crystal phase of silicon carbide would affect your calculations and can be used for other polytypes because it's highly polytypic?
Yeah, sure. It will change the constants of the CC layer, boundary layer, but there are some difficulties to understand the thickness of the layer. So I think that the main results won't change. Maybe some slope of the dependence of the biaxial modulus on porosity will change. But we have other questions about the structure that should be resolved before that, before we end.
Thank you. Alexei, please, yes.
Yuri, thank you for your nice talk. You said that during calculations, the pores were placed at random places. I would like to ask, how sensitive the final result to these random positions? I mean, how large is the deviation of the result from the mean value at different runs?
I said about statistical fluctuations, so it's no more than 3% of deviation for 10 models. I mean, 10 geometries.
Okay. Thank you.
I don't see any further questions, so let's thank Yuri again.
Thank you.
So the next talk will be presented by Dmitry Mitin, and it's on flexible and transparent electrode based on patterned single-wall carbon nanotube layer.
Hello, dear colleagues.
Hi.
Do you see my screen?
Not yet. Yes, we can see it now.
Okay. Okay, my name is Dmitry Mitin, and I'm from St. Petersburg Academic University. And today I want to talk about flexible and transparent electrode based on patterned single-walled cabin and tube layers. Everybody knows that transparent electrodes are used in different applications such as solar cells, LEDs, touch screens, and in other modern smart devices. Today, usually metal grids and conductive oxides are used as transparent electrodes. Also used some new materials such as conductive polymers, graphene, and silver nanowires. But all of these electrodes has some disadvantages, which you can see on the screen. Single-walled cabin and tubes can be a good replacement for conductive oxides and metal grids because it has very outstanding properties such as transparency, chemical stability, price, and flexibility, but we have some problems with conductivity. So CNT have high optical transmittance, but how to increase conductivity? In this work, we will speak about layer patterning, which can be used to resolve contradiction between transmittance and conductivity. To compare different transparent electrodes, usually used value figure of merit. Figure of merit is a value that evaluates and compares the optoelectronic performance of different TCs. And you can see that figure of merit derives the formula for equivalent resistance showing the sheet resistance of the film in the case of 90% transmittance. And we can compare this R90 for different transparent electrodes. And you can see that ITO on rigid substrate has 10 ohm per square, and cabin and tubes has only 25 ohm per square, and it is far from ITO. We try to resolve this problem. In this work, we discuss a model of patterned electrodes. We used a fill factor which connected with period of the grid and the width of the stripes. The grid transmittance T, the transmittance of patterned electrode which connected with film factor, and transparency of initial continuous layer. Sheet resistance of transmittance electrode, and initial transmittance. Using these formulas, we get the relation between transmittance and sheet resistance for the patterned CNT layer. And here we can see the dependencies of transmittance versus sheet resistance for different fill factors. And we can see that to get some sheet resistance for different fill factor, we should use films with different transmittance. And okay, next we want to discuss the choice of initial transmittance of continuous layer for making of patterned layer. This graph shows the dependence of initial transmittance of CNT layer versus sheet resistance. And you can see that if we will use initial layers with low transmittance, we can improve properties of patterned electrodes, compare it with properties of continuous layer. It is a white area, and gray area is where properties of patterned electrode is worst properties, not better than continuous layer. Next, we will discuss the experiment. We used CNT layers, which were produced in Tech University by the group of Professor Robert Nasibulin, and we deposited it on transparent glass substrate. After that, we doped by gold chloride and densified it by isopropyl alcohol. We used the combination of optical laser lithography and dry etching in oxygen plasma to form grids. We got grids with different width of the stripes, but with the uniform, to ensure uniform transmittance, we used different width of the stripes. Next, we made experiments with Raman spectroscopy, which show that there is no damage of our CNT electrodes after different procedures of our processing, such as densification, photoresist spin coating, etching, photoresist removal, and doping of films. Here you can see optical transmittance spectra of initial CNT waves with different transmittance, and final spectra of patterned electrodes with transmittance of 95%. Everybody knows that today is very popular and flexible electrodes, so we transfer our patterned CNT layer on flexible polydimethylsiloxane matrix, and after that we made band release test. We put this flexible electrode on quartz tube with different diameter, and so we changed the strain and see how changing the relative resistance, and we can see that relative resistance is not exceed 4%. That is very good result for flexible patterned electrodes, comparable with the best published results. And here you can see the final graph of our modeling. Green color shows the best results, the best known results for continuous layer, and here we show that if we will use for patterning continuous layer with low transmittance, we can get films, patterned films with very low resistance, lower than ITO on rigid substrates, and with low fig of merit. So this result is comparable with ITO on rigid substrate, and this technique can be used for producing highly transparent and conductive patterned electrodes. Thank you for your attention.
Thank you very much, Dmitry. Can you hear me now?
Yes.
Are there any questions in the audience? Okay, so may I ask, what is the doping material and what is the typical doping level in your studies? Because you mentioned doping.
It is hard to say about, it's not classical doping, it is doping which works like, it's just like chemical doping, it's not,
okay.
not traditional
Mm-hmm.
doping like in semiconductors, yes. It is doping based on chemical reactions between oxygen, which contains in gold acid. I'm sorry, I forgot name of this chemical. Yes, and I can say that conductivity of single-walled carbon nanotubes increase in 3 times after this procedure.
Mm-hmm. Thank you. Other questions? I don't see more questions, so let's thank the speaker again. So we are moving to the last talk of the conference, which will be given by Sebastian Shepenkov, and it's on dislocations and the intersections as luminous quantum wires and quantum dots in gallium nitride.
Hello.
Hello.
Could you tell? Can you see me? And
I can see you.
Okay.
We just need your screen.
Okay. Okay. Can you see my screen?
Yes.
Now?
Yes. It's fine.
Okay.
Please start.
Hello again. My name is Sebastian Shepenkov, and I will talk about luminescence of introduced dislocations in gallium nitride from perspective of quantum dots and quantum wires. First, I will discuss a little bit dislocations as 1D and 2D quantum systems. Then I will give overview of experimental settings very briefly. Then I will speak about previous results and present some new ones. And of course, I will do a conclusion. Dislocations are linear defects in crystal structure, which exceed which exceed unit cell parameters by many orders. They can be up to tens of microns. And along their lines exists a strain field, which becomes macroscopic. Thus, they can be considered as one-dimensional quantum wells and can be expressed like on this diagram. Also, there exists polarization along their line. And in spectra, if we speak about dislocations that have radiative properties, it usually are presented like a single narrow line. But there is also another feature of the dislocations. They can dissociate. So if we talk about perfect co-dislocation, like on the left picture, we will have one D system with one dislocation line. But if we if dislocation is dissociated, like on the left pictures, there actually would be a more complex structure. It would have two partial dislocations, which are shown here with this symbol, and between them will be the area of the stacking fault, which is a break in the order of the layers in the crystal structure. And this dissociated dislocation, it can be both 1D or 2D system, depending on the parameter called dissociation width, which is distance between two partial dislocations or width of the stacking fault. Also, there is an interesting feature of stacking faults in wurtzite structure, which is a structure of the gallium nitride. So if you have a stacking fault in wurtzite lattice, it would be a segments of sphalerite phase or of a cubic phase, which has a smaller band gap, thus making it kind of a natural quantum well, if it exists. And also, usually, if we consider non-polar lattices, we have this classic quantum well with smoothed walls. But in Wurtzite structure, we have some lattices which are polarized. So we would have this triangular shaped quantum well. And it will be characterized in spectra with a doublet or triplet fine structure, and usually of these peaks of different components of different intensity. These systems used in production of LEDs, I believe that direct growth of quantum wires was discussed a lot in this conference. So here I show two different approaches for acquiring these systems for LEDs. The first one is the use of patterned sapphire substrate for growth of gallium arsenicum pyramids with utilizing the capillarity-induced alloy segregation to acquire quantum wire, quantum dot systems. But it has its downfalls. It is a rather complex process, and also it gives a low density of these structures. Another way is to acquire quantum wires is overgrowth of two quantum well systems. It actually gives better quality properties, so better density of these structures, but it is also inefficient economically. But by later studies, it was discovered that for gallium nitride, which is a direct wide gap semiconductor, and which is already used for production of LED and other electronic devices, it was discovered by different groups that in these crystals, if we introduce mechanically dislocations, they will have native luminescence, and from our perspective, this studying of this luminescence, its properties, can be used for developing a new kind of LED technology of understanding problems of existing ones, because these dislocations make a very peculiar object for the studies. So this is a very brief overview of how we perform our experiments. So first of all, we need to introduce dislocations in gallium nitride crystals. We do this by scratching or by microindentation. As you can see in this picture, there are bricks of the nano-indenter. Then we study the luminescence and polarization using photoluminescence and photoluminescence techniques. And we also study the core structure using different transmission electron microscopy techniques. So here in this slide, it was demonstrated as how it was discovered at room temperature. As you can see, there are two scratches which introduce sets of dislocations, which have, as can see from the spectra, luminescence exceeding one of the near band edge emission, which make it which was considered by my colleagues as potential candidates for ultraviolet LEDs. If we study this luminescence at liquid nitrogen temperature, we can see that peak that was on the previous slides, the dislocation-related luminescence peaks, has a doublet fine structure with two peaks with different intensity. Also, for intersection points of dislocations, there is another emission, which was called intersection-related luminescence with a single narrow peak. And from the data from previous studies of different Wurtzite type semiconductors, it was considered that DRL is from the shaded dislocations, and that IRL is from the extended dislocation nodes. So in TEM studies, this assumption was proved. As you can see in this picture, we have this actually is a dissociation of the introduced dislocation in gallium nitride with the formation of staking fault. Also in the cross section, it was discovered that these partial dislocations have different atoms in their core. One has a gallium atom in its core, and another one has a nitrogen in its core. And also in polarization studies, it was discovered that two components of the dislocation-related luminescence doublet have different polarization against dislocation line. Thus, we can conclude that these dislocation lines can be considered that as quantum wires, 1D systems, because their dissociation width is 5 nanometers, which is around, which is close to the radius of the exciton, and also that we can explain doublet structure with that different atoms are in course of the partial dislocations. No, these were previous results. New results are about extended dislocation nodes. One is shown here, triangle shape in this picture. So extended dislocation nodes have rather bigger size than dissociation width. It's around 30 nanometers. So from our point, from first look, it appears that this should be considered as stacking fault, as luminescence of the stacking fault, also because we thought so because its spectrum position 3.3 electron volts is very close to the position of the studied of the true E2 stacking faults that were intentionally grown in the gallium nitride structure. Thus, it was thought that it is a 2D system, but it needed proving. So to understand what type of system we have with intersection nodes, we used non-indentation to create, as you can see in this CL wavelength, long dislocation branches around 15 nanometers, and their luminescence here is shown with yellow and orange, is close to linear. And we have these branches are well separated from each other if we use the Berkovich tip, and we also have a satisfying density of the ERL spots, which are green in this picture, which we can study more closely. So we will look at two branches, one on the next slide, which is shown here, and one in the after that slide. Numbers show numbers of the slides. So in the first slide, you can see the technique, the use of the technique that is called line scan. Line scan, it's a diagram that is built by summing all the spectra along this line and then putting it against distance from the prick, from the indentation prick in this direction. And in diagram with color is shown intensity of this summarized spectra at concrete wavelength. As we can see that with the distance from the indentation, we have a gradual redshift of dislocation-related luminescence, which follows near band edge emission. This is because of reduce of mechanical stress with distance from the non-indentation. Also for the intersection-related luminescence, we see the same trend, but it is discrete. On the other hand, if we look at another branch and we look at particular spots, we can see that despite these spots, this spectra having also red shift of the middle position, gradually with the distance. We can see that the affine structure changes irregularly. So in some spectra, we have a single narrow peak, like in the spectrum number 1, and this peak is actually characteristical for this area. In the spectrum number 2, we have a well-resolved doublet with 2 peaks in the ERL position, which is characteristical for this region. And in the end of the dislocation branch, we have a spectra like in the third one, with a single strong peak and with weak peak, with worsened separation of the doublet. So also here we can see that full width at half maximum of these peaks is different, is smaller or bigger if compared to the full width of half maximum of near band edge emission. We also have, if we have separation for intersection related luminescence, we can compare it with the separation for dislocation related luminescence. And as we can see for dislocation related luminescence, this separation is constant despite distance from the indentation or scratch or even temperature. It remains around 35 millielectron volts. But if we look at the same property of the intersection related luminescence, we can see that it changes regularly with distance, and it can disappear and appear, and also separation isn't constant. These properties couldn't be only explained by intersection related luminescence only by reduce of the mechanical stress. This can be explained if we consider sources of intersection related luminescence as a system of quantum dots or quantum dot-like system these quantum dots, the fine structure strongly depends on the geometric parameters of these quantum dots, as can be seen in this graph. From our structural studies of these dislocation networks, we know that extended dislocation nodes not only vary in sizes, like shown here, but also they vary geometry. So here we have triangle nodes, and here we have a double triangle node. And they can appear in different amounts. Here we have like a single node, here is a single node, here we have 2 nodes very close to each other. If we consider these properties of extended dislocation nodes and consider them as sources of intersection related luminescence, since we can see that the emission will be strongly dependent on the amount and on the sizes of the nodes that was in the generation region of the technique that we use for studying luminescence of this structure, which coincides with the assumption that the TRL is luminescence from quantum dot-like system. So to sum up what I have told, we have dislocation-related luminescence with 2 bands. One is dislocation-related luminescence or from dislocation lines. Another one is from the intersection points. Dislocation lines behave like 1D quantum wires and have their properties, also with polarization due to the website structure being polar. And extended dislocation nodes, previously considered as 2D systems, actually are 0D systems and act like quantum dots in luminescence and also in structure. Thank you for your attention.
Thank you very much, Sebastian. So are there any questions? So would you approach work for other materials other than gallium nitride?
I also study gallium oxide.
Okay. And is it also worksite? I don't know.
No,
Gallium oxide.
it has different phases. One of them also has a Wurtzite-like structure. It's also this HCP. Oh, the hexagonal closed spectrum.
Thanks. Frank, please.
Do you observe only these screw dislocations, or are you bothered by other types of dislocations in your scratched or indented samples?
Thank you for your question. We actually it's a complex structure, so it's from the indentation point. I have here pictures suitable. No, I don't have them. Sorry. But from the indentation point, it goes as 8 screw dislocations, and we can have different sets of dislocations. One of them called basal set, which light in the basal plane. They end with edge dislocation in the basal plane. So it's like 2 dislocations go in this direction, and they are like closed with the edge dislocation. Also, we have prismatic sets, which also end with edge dislocation, but it goes to the surface in the prismatic plane. And of course, we have to consider contrasts and influence of the ground-in threading dislocations.
So does it mean that you have to do your studies sufficiently far from the indentation point to select these screw dislocations, or is it irrelevant?
We actually study them along the whole branch. So we look in these and these areas together. Edge dislocations are usually in this region. Here we have A screw dislocations, which I'm interested in.
Thank you.
I don't see any further questions, so let's thank Sebastian again, and let's thank all the speakers over the session and all speakers over the conference. So with this, the conference program is over, and I would like to thank you all for participating in the conference and presented talks. So we have had 15 invited talks from 8 countries: France, Germany, Poland, Denmark, Sweden, Canada, Switzerland, and Russia, and 24 oral talks altogether in 3 days or 2.5 days, presented mainly by younger scientists. And I should say that I enjoyed most of them. Some of them I enjoyed very much. So again, thank you very much, and I wish you all future success, and please stay safe and healthy in this time. And I hope to see you all and welcome you all in Peterhof one day or another. Frank, do you want to add something?
I would add that at this point, we should congratulate you and your team noisily for organizing an exciting program and having a very smooth conference.
Thank you.
Maybe we cannot be that noisy from the distance, but we congratulate you.
Thank you very much for the organization, and to the young people. The talks were excellent, high level. So thank you very much.
Thank you. So, yeah, see you soon, and we'll be in touch. Yes, thank you very much. Bye-bye.
Thank you.
Bye-bye.
Thanks, everybody. Goodbye.
Bye.
Thank you.
Bye.
Спасибо большое, Ксения. Ну вот мы закончили. Всего доброго.
Да, пожалуйста, спасибо вам большое. Было очень интересно.
Спасибо.
Всего хорошего.
До свидания.
До свидания.